So those things are critical.
Okay, I think we can start then. So today we have Statistical here, who's now in Oslo, at the ITA, and he did this. So he's working at Boltzmann now since summer, as far as I understood, last year, and he did his PhD at the IAP in Paris. However, he still seems to be interested in moving to some other places, like here at the postdoc as well. And today we're going to hear about linear evolution of quantum background communication.
Okay, so thank you very much for inviting me. I'm very happy to be here. I've never talked with such equipment. So I'm going to talk about the nonlinear evolution of the cosmic microwave background. So first I will review the nonlinear perturbation theory as a general framework, and I will explain also the motivation for working beyond linear order in perturbations. Then I will detail the formalism to deal with radiation, and especially formalism to deal with polarized radiation in the third part, and also how we can make a multipolar expansion using symmetric trace-free tensor, how I think it's much easier. And then I will turn to a part which seems to be 1/5, but actually it's bigger, which is the approximate resolution of the equation in order to understand the nonlinear dynamics.
Can you repeat what STF is?
STF, symmetric trace-free tensors, multiples. So the main motivation for working with nonlinear perturbation theory and nonlinear evolution of these perturbations is comes from the Wick's theorem. If you look at the Wick's theorem for a purely Gaussian field, what you find is that for an odd number of field, the statistical average is 0, and for an even number of fields, it can be expressed only using the two-point correlator function. So that's the main idea. Now, the predictions that the theoreticians make about the early universe are expressed in terms of the statistics coming from the quantum treatment of the primordial curvature perturbation, which is zeta. And it can be separated into a part which is Gaussian, which comes from the linear perturbation theory, and a part which is non-Gaussian and which can differ really, really strongly from one model to another. So zeta 1 is the first order perturbation, and zeta 2 over 2 is the second order perturbation of this zeta function. And in most models where these parts come from a nonlinear coupling during inflation, zeta 2 can be expressed in terms of a convolution over a certain kernel of zeta 1. And this kernel, which is called usually in the literature FNL for NL nonlinear, is one of it's the prediction in terms of non-Gaussianity of all inflationary models. So what people want to measure is this, because then they could constrain the theory of inflation. Now, what happens is we don't observe directly the curvature perturbation zeta at the end of inflation, but 14 billion years after, we observe the temperature in the CMB. Or we have other tools also to observe the universe. But the main tool that we use is the CMB for non-Gaussianity here. And again, there is no reason for this function to be linear in zeta. So at first order, of course, it doesn't matter, because then we can expand this very general relation into a first order perturbation of the temperature being a linear function of the first order curvature perturbation. But at second order, then you'll see that we have two terms. A term which comes from the second order of zeta itself, but also a term which comes from the fact that t is not a linear function. So we have a term which is a linear evolution of a non-Gaussian field, and a term which is a non-linear evolution which is quadratic in Gaussian field. Now, just expressing Fourier space, that's how it treats. The temperature fluctuation. It's for a given mode k, it's transfer function multiplying the primordial Gaussian field. But at second order, it's a linear transfer function multiplying the second order curvature perturbation, and a convolution which depends on time. Here I should have put eta today just to state that it depends on the time that has passed, and the quadratic in first order Gaussian fields. So what people want to measure, that would like to measure, is this, but then the signal will be followed by this term. So my main question is, how big is this, and how big is this, and in which range of values And I will show that this signal is dominating, and in which range of values this part of the temperature is dominating. So the main tool then to observe non-Gaussianity is one of the tools is the three-point function. And you see that because of this non-Gaussian term here or here, then it's non-zero because we have some contribution of θ1, and θ2. But this θ2 can come either from here or either from here. So that's what I'm stating here. It's coming either from a primordial FNL or from a nonlinear evolution term. And now, from now on, in my talk, I'm going to talk about this nonlinear evolution. Yes?
Is there any way to clean the second term out from the first term, or is it sort of an unremovable?
Sorry?
Is there any way to clean the second term out from the first term, or do they combine in an unseparable way?
Well, in order to clean it, you need to know what it is. That's my point. So yes, it's for sure that if you know what what is the nonlinear transfer function, you can surely subtract it and then just get this. That's the whole point of finding this nonlinear evolution. Yeah, yes, it's not a.
How do you know
That it's possible to do it?
I guess if you knew t nonlinear and you knew zeta sub k1,
Yes.
then you could do it. But how do you measure?
So which we measure is the sum of the two. And then from the first order, let's say constraint on your model, then you can know what is θ1 and know what is the nonlinear evolution. So you do by iteration at first order, just by linear perturbation theory. You go into Boltzmann or Planck, you have all these constraints, so you know the history of the universe. You say, okay, in the history of the universe, then the nonlinear evolution has to be this. And then, just for the non-Gaussianity, yes, I didn't mention, the important point about this three-point function is that it's zero exactly in the linear perturbation theory. So the first order where this is going to be non-zero is when you use nonlinear perturbation theory. So yes, use linear perturbation theory to infer this, then you can put it back in the three-point function. So now, I said I will talk about the nonlinear evolution. So let me just spend a few slides on the description of perturbation in cosmology. So perturbing in cosmology, or at least in GR, or in any manifold, it's not as simple as let's say perturbation in quantum field theory, because the background is you're not perturbing things around a fixed background. So you want to give a meaning to the perturbation of the tensor, which is a physical tensor minus a background tensor. But the problem is that the physical tensor lives in a perturbed spacetime, or a physical spacetime, some manifold, and the background tensor lives in a different manifold. So you cannot make such subtraction if you don't give a meaning to this difference. So the main idea, which is not from me, which is from the mid-90s, is to embed the manifold into a 5-dimensional manifold, that is 4 plus 1, and then you will have a stacking of slices of space-time. You begin by the background slice, end up with a physical space-time, and in between you will have all the slices of all intermediary space-time. And then, with this embedding, you can identify points between the background space-time and the perturbed space-time just by using a field that from now on I will call a gauge field, which has a non-vanishing last component. So it means that the integral curves of this field are going to cross from this slide to this, from this slice to this slice, and as a consequence, all the points lying through this field, so I'm going to show you the picture easier. All the points lying through this field, will give them the same coordinate. We'll say that it's the same point, because in the end we will only work on the background spacetime. But as you can already see on this picture, so here it's my 4-dimensional background manifold. Here it's my perturbed 4-dimensional manifold. And here it's the gauge field, so integral curve of a vector field. And then I will just identify this point and this point. If, as a gauge field, I take the continuous line. But as you can see directly on this plot, then it's really clear that you could choose another gauge field, another way to identify a point. And that's exactly the meaning of the gauge freedom. It's just because you identify points in a manifold with an extra dimension then you have a freedom in the way you identify the points, and that's the gauge freedom. So I've done these two plots just to show that this gauge transformation, so when you go from one way to identify the points to another way, it's clearly different from just change of coordinates. Because here, you see, the first identification, I have a set of coordinates like here. I've asked for x. The second gauge, I have a set of coordinates that I've called y. But I've changed the point here, but I haven't changed the point here. But here, on this plot, I just keep the same gauge, but with the same gauge, I change the coordinates, so I can give different names. These names are x, names are y, but the way I identify the point is fixed. So that's why when you do a gauge transformation, it looks like a change of coordinates, but it's intrinsically different from a change of coordinates. So now that you have this, sorry, I'm coming back to this slide. Now that you have this way to identify the points, what you do is all the tensor you have on the third spacetime, you have a way just by pulling them back, dragging them back, to carry them on the background spacetime, and now they will live on the same manifold, and now they can make the difference. And the way to carry is the pullback, as I said, and the pullback can be expressed in terms of the powers of the derivative. So you'll see that the difference between the pullback tensor and the background tensor, it's a perturbation, but this perturbation naturally splits into orders because you will have the first power of the derivative. You will call that the first power perturbation. The second power of the derivative, and it will be the second order perturbation, and so on and so on. So that's the reason why you always find in cosmological perturbations that there are orders of perturbation, and they don't consider cosmologists the total perturbation. They prefer to deal with orders of perturbation. So now, how do we deal with this problem of gauge dependence? Well, the usual way to do it since the early 80s is to form a set of gauge invariant variables. So to combine the gauge dependent part of the tensor in a way which is gauge independent. And since an equation can always be recast on an equation, it's a statement that some tensor equals 0. So just think that the Einstein tensor is g equal t, but you have to think of it as g minus t equals 0. So it's a tensor which is 0 there, which is 0 there. So no matter how you pull it back, the difference between the perturb and the background equation as a tensor will always be 0. So it means that since the tensor is 0 everywhere, it's gauge invariant. So if you can find a set of gauge invariant variables, so that's the key point. You need to find a set of gauge invariant variables. But if you find a set of gauge invariant variables, then you're sure that your equation will eventually be expressed only in terms of gauge invariant variables. So that's one part of perturbation theory, building these gauge invariant variables. So this has been done in the 80s for first order perturbation, and it can be shown that it can be done at second order and even at higher order. Sorry?
No, I was saying that to some extent it's not necessary to necessarily construct.
No, it's just a point of view. You can fix the gauge.
You can fix the gauge.
And then if you want to know the result in another gauge, you change the gauge. It's just a matter of how you want to think the gauge transformation. It's completely equivalent. But in the end, you still need to understand how things change in the gauge.
It's just when you fix in the gauge, you need to be sure that you completely fix the gauge.
Exactly. So that's a way to be sure that you fix the gauge. So, and the other point coming from the fact that we have first order, second order perturbation is that we have a hierarchy of equations. At first order, the first order perturbation satisfies a linear equation. At second order, this is very important. It's at second order, they will satisfy the same equation, that means the same linear equation, but supplemented with a source term which will be quadratic in first order perturbation. So that's the key to solving actually all the others, because if you can solve at first order, then you know the independent functions which are the solution of this equation, and you can plug it back into the second order equation, which is, since it's the same equation here, I mean formally, then you can use the green function method just to integrate over the sources and find the result. And Of course, it's very difficult at third order, but at least formally it's possible at third order to do the same. We'll have the same equation for third order perturbation and then source term involving lower orders. So this is a very this is a method which eventually works. It's just that it's very time consuming for calculations by hand. So now I'm going back to the evolution of radiation, my problem. So I said that I wanted to know how radiation evolves non-linearly in time. So there are two ways to describe the matter content of the universe, or the matter content of the physical problem. Two main ways, let's say. There is the free approximation, and then the statistical description, or kinetic theory. So the free approximation, you need to know the pressure, the energy density, the velocity of your fluid, and if it's not a perfect fluid, it has some you have a layer which will act upon another layer, and we have an isotopic stress. So from Bianchi identities, what you get directly is that the stress energy tensor is conserved. So this means that you get an equation for the evolution of the energy density. From the earlier equation, you get an equation for the evolution. I should have put it different. In the conservation equation, you have the evolution of the energy density in function of the velocity. From the earlier equation, you get the evolution of velocity in function of the anisotropic stress, but then you have nothing to tell you what's the evolution of the anisotropic stress. So that's one of the limits of the free description. What's the expression and what's the evolution of the anisotropic stress? And also, I didn't put it here, but you also have the pressure. You need to relate the pressure with the energy density. So you need to know an equation of state. And last, and that's actually very important in cosmology, this is only valid for the total fluid, the conservation of the stress energy tensor. If you have several fluids, then each one of them will be independently not conserved. So they will have a force, they will act upon each other. So each one will have a force here on the right hand side. And what is the force? Then you need to work this out from the microscopic physics. So that's why we go to the statistical description or kinetic theory, because then we have the answers for this problem. But I should mention that in the case of cold dark matter, you know the equation of state, it's W equals 0. There is no anisotropic stress. Since it's dark, there is no interaction, so there is no force. So for cold dark matter, for instance, the free description is perfect. Now for radiation, we know the equation of state, but we don't know what's the evolution of the anisotropic stress and what's the force acted upon. So what we do, we use a distribution function, which is the probability of finding particles in at a given position, space-time, for a given momentum. And since we want to have a physical meaning to this, to the components of this momentum, we use a local Minkowski space-time. That is, we use a tetrad, a local set of orthonormal vectors, in order to extract components in this momentum. So we can split it into magnitude, which would be the energy of a photon, and a direction, which is the direction of propagation of a photon. And of course, this description is more general than the field description, but you can recover the field description just because you can build out of this function, you can build a stress energy tensor. Now, for the field description, the conservation of the stress energy tensor gives you conservation equation. For the statistical description, it's the Boltzmann equation, which tells you how the distribution function evolves with time. It's formally reads like that: the Liouville operator on F equals the collision term on F. So the Liouville operator, it just states that particles are free streaming; they just propagate on geodesics. So what you need to express this Liouville term, it's actually just the geodesic equation. And for the geodesic equation, the only thing you need is the connection on this hand. That's what tells you what going straight means. And on the right hand side, you need to know the collision. So in the cosmological context, the collision are on free electron. So it's mainly constant scattering on free electron. So this is general. It's not perturbative. Now, if we want to perform a perturbative expansion, what we need to know is only the perturbation of the connection. Why? Because I just said that in the Newville operator, we just need the geodesic, and in the geodesic, we just need the connection. And the connection derives just from the expression of the tetrad. But since the tetrad are just defined with the metric, they are defined through their normalization, actually the only thing we need is to know the perturbation of the metric. So what I mean is everything comes from the perturbation of the metric, and you go all the way up to perturb the Liouville term. Now, what about the collisions? So I'm sure you have seen this plot several times, but I want to comment on it because it helps understanding what happens. So you know that when there is a quadruple anisotropy, that is you have one direction which has more intensity than another direction, you know that after tungsten scattering, there will be polarization. Why there will be polarization? Because tungsten scattering selects only the part of polarization which can propagate in the outgoing direction, orthonormal to the outgoing direction. So you see this part propagates because it's going to stay orthonormal, but not this part. And here it's the contrary. It's this part which doesn't propagate and this one which propagates. And just this fact creates polarization. So this means that we cannot just rely on a scalar value distribution function, which gives you the position and the momentum of particles. We also need to describe their polarization. So what we're going to do, instead of having a scalar value distribution function, then we'll have the tensor value distribution function, which will encode the probability of finding a particle at some point with some momentum with some polarization. So it's given by the scalar value distribution function multiplying the tensor product of the polarization vector, and the polarization vector is taken in the Lorentz gauge, that is orthonormal to the momentum. And an essential tool in this formalism is the screen projector. So you probably already know this projector. So if you have a given operator, which is, if you have a given observer whose velocity is E0, that's the time artifact, then you know that G mu plus E mu, E nu will be a projector in the spatial slices, so something which will select spatial momentum. But then if you add also minus N mu, minus N mu, N nu, then it will also select spatial slices, but orthonormal to the outgoing direction. And that's why it's called a screen projector. And the key point is that if you screen project the polarization tensor, polarization vector, then it's no more dependent on the electromagnetic gauge. So it's not the same. It's not the same gauge. It's not the gauge for perturbation. It's the electromagnetic gauge. So, which means that this quantity, naive quantity, it's still electromagnetic gauge dependent, but this quantity, which consists in taking the previous one and project with the screen projector, no longer depends on the electromagnetic gauge choice. So it has all the degrees of freedom, no more, no less. And that's the quantity we're going to work with in when we want to describe polarized radiation. So if we count the number of degrees of freedom, what we find is that F is an Hermitian, is a complex tensor value function. So it has only, in the end, because of the fact that it's screen projected, it has only 4 degrees of freedom. And so just for you to visualize what it's physically, if you take an outgoing propagating direction, which is along the z-axis, like n1 equals 0 and 2 equals 0, then that's how that's the expression of the screen projector, and that's the expression of the tensor value distribution function. And here you recognize, now I'm in contact with optics because you recognize the Stokes parameter, I, Q, U, and V. So if you want to express this just in the covariant form, that's the way it's expressed. So I is the intensity, so that's no matter the polarization, it's the number of photons, the energy actually. V is the degree of circular polarization, and P mu nu, which takes only Q and U, and not I and V. It's straight phase, and symmetric straight phase, and it's the degree of linear polarization. So in cosmology, we'll see that there is no circular polarization, so we only deal with I and P mu nu. Now, it's the same as for a scalar value distribution function. Instead of having a scalar value Boltzmann equation, now we have a tensor value Boltzmann equation. So it is essentially the same. In order to derive the Boltzmann equation, the only element we use is the geodesic equation. So particles are propagating on geodesics. Now, for polarization, particles are propagated along geodesics, and the polarization vector is parallel propagated. Using just these two features, we can show that the Liouville equation separates the evolution of intensity, linear polarization, and circular polarization, which is important because that's one of the reasons why there is no creation of circular polarization, and why we can treat intensity and linear polarization separately. Now the collision term, here I haven't written the entire collision term, which is rather complicated. I've taken only the limit where, the Thomson limit where we can neglect recurrent terms, which are here, I didn't write them, and also for cold electrons, that is electrons which have no bulk velocity, are just standing there. And the collision term has this very simple expression, so I'm going to explain why this is very simple. It can be understood physically quite easily because what it says is that the collision term, you just take all the possible incoming direction, and you know that in the outgoing direction, it will only select, as I shown in the drawing, it will only select the polarization which can propagate orthonormal to the outgoing direction. That's what this projector says. It says take the incoming direction, but then only the part which will project correctly can contribute to the outgoing direction. And then, of course, you subtract all the possible collision which will take a photon going in some other outgoing direction. So it's just a balance of what is incoming and what is outgoing, but not everything can come. Now, if you want to recover the standard Thomson cross-section, it's very simple. It's just instead of having a tensor value distribution function, you just say that there is no linear polarization, no circular polarization, so just an intensity. And if you plug it back, then you can show that this expression actually boils down to 1 plus cos square theta, where cos square, well, theta is the angle between incoming and outgoing direction. So you recover the standard formulas that you find in textbooks about Thomson sketching. Now, if you want the exact collision term, you cannot just assume that all electrons are cold, but what you do, you calculate the collision term for each one of these electrons in its reference, in its rest frame, and then you just sum the result in some average frame.
Your last term on the second line,
yeah,
the above that circular term,
yeah,
the I/2, is that D supposed to kind of, some would say Levis beta on an E epsilon D CAB, or is that an O?
This D?
No, yeah, that's D up there, and is there a D on the Levis beta next to it?
So this D is just formal, just to state that it depends on the vector, but it's not.
There is no G among low India.
No, there is zero CAB.
Zero, I think
Zero.
that's the
It means that it's projected
time-like.
time-like. Yeah. No, this D is. I should not have put A here. It just means that it depends on the vector.
Yeah.
I could have put boldface instead, just to give them. Yeah, I should put boldface actually. So that's not the formalism that is usually used in the textbook. That's why I've been explaining it. It can be considered as being more complicated. Actually, no, it's a lot easier when you want to go to nonlinear perturbations. The reason is that you can make use of computers to help you in your calculation. So then a natural way, or the easiest way to use the computers in the calculation is to, instead of performing directly a multipolar an expansion in spherical harmonics for the dependence in the direction, I performed an expansion in symmetric trace-free tensors, which is equivalent, as it's well known. So I decompose the dependence on the energy and the direction in some multiples which depends only on the energy and contracted with direction. These multiples can be extracted with the following integrals. And for the degree of linear polarization, yeah.
Can we go back?
Yeah.
Why is in this integral, projection integral? Why is there an average A?
No, sorry, it's a notation for a symmetric trace-free.
Okay.
Take all the possible. So it's AL underscore is my notation for a multi-index.
So
it means several indices, and then in the several indices you take the symmetric trace-free sum. Because the multiples have to be symmetric trace-free.
Yeah, sure.
So
No, I sometimes needed this notation. How is it standard one? To use angle brackets.
Most of this formalism was developed by Anthony Chaliner in 1999, and that's his notation. So since there is very few papers on it, I didn't want to add in a new notation, so I just took the same. Now another notation is to put a hat on it. So for gravitational waves, in the primitive gravitational waves, that's a hat. So for linear polarization, it's the same. We can expand it in multiples, but the difference is that now it's a tensor valued function, so it's not just we don't have just one kind of multiples. We have electric type multiples and magnetic type multiples. So what is interesting in this procedure is that we go directly to these electric and magnetic type multiples, whereas in the usual treatments we have to use intermediary steps before going to electric and magnetic type multiples. And it's a bit similar to for the intensity. We have some integrals which give you the expression of these multiples out of the tensor encoding the linear polarization. So let me summarize all what I just said about the method. So far I didn't show you any equation. It's a very big expression. But what's important is the method. So we start from perturbing the metric, and I explain what it means to perturb the metric with this embedding of space-time. So in practice, we choose a gauge or form gauge interval. From this metric, we deduce the perturbation of the tetrad. In practice, we also have some freedom in choosing the tetrad, local Lorentz transformation. Then from the perturbation of the tetrad, we deduce the perturbation of the connection. From the perturbation of the connections, we can find the perturbation of the geodesics. And from this, the perturbation of the new beam. Now, after we work out the collision term, we compute the collision term for each electron in its rest frame. And then for all electrons, we carry in the cosmological frame and make a sum over the distribution of electrons. This is very general, it's not perturbed so far. So then we expand in perturbation. That is, we said that there is a background intensity, a first order intensity, a second order intensity. The same for the degree of linear polarization. There is a background linear polarization, first order linear polarization. But what happens is that there is no background polarization. So that's a lot easier for polarization. Then we expand in multiples because we want at some point to have a set of equations which are easy to integrate. And then that another big part is to solve it. And since you have a set of equations which contains all the multiples, then you have to solve it numerically. So what I used to do that, I used the fact that the only thing that you really need in your calculations are these integrals on directions. And what is really good is that if you have an odd number of directions, if you integrate over the sphere, then it's 0. And if you have an even number of directions, it's a combination of the metric. So just by using a package which can perform abstract tensor algebra, then you can automatize all these integrals and also all these symmetric trace-free combinations, which are, if you expand them, are really huge. Then they are worked out by the computer, so you don't need to do everything by hand. And I also worked out the perturbation using abstract calculus package, just to cross-check what I could find the back end.
So exact is tensor manipulations.
Yeah, exact.
And
it's also called extensor.
Yeah. And who wrote expert?
Expert? It's the same as exact. So exact has all the main functions. Yeah. It's a very general package for handling you define tensor, you can contract, simplify. Right. Expert is using the tools of exact just to solve a particular problem, which is perturbing the metric to elements or
So it's particular
so
parameter.
you need to load this and then you need to load this on top of it. But it's using the functions defined. So it's yes, it's the same order.
But it is left-hand side. It is method perturbation.
Yes, exactly. That's for the question. Now, of course, for numerical integration, it's a lot better to have spherical harmonic components rather than symmetric trace tensor. The main reason being that in cosmology there is this assumption of statistical directional statistical independence. So if you want to use this, what you can do, you can align the mode you consider with the direction of the spherical harmonics, and then you have a lot less equation to solve. So that's the main reason for working with the CITA LM or ILM rather than the multiple associated to the intensity. So we do this for intensity, for electric type, magnetic type, and this the conversion is given by these functions, this tensor, sorry, which once contracted with the symmetric trace tensor give you the spherical harmonic components. And backwards, if you sum over all the m for given L, then you can build the corresponding symmetric trace tensor.
If you had some term which violated chirality or something, could you get a circular equivalence in here?
Sorry?
If you had some way of generating circular polarization.
Yes, circular polarization is a scalar. So it's formulated to be the same thing as I. So it's, the way, for instance, to develop V, it will be the same expression as this, just putting just putting V instead of I. So I don't show you the equations because they are quite involved. They've been attempted to do very happily. Now I'm going to talk about what's more important. Is now that we have the equation, we need to answer the question: is it important or not as an effect? Because that was my first question. Nonlinear evolution, is it important or not? So, since it's very involved and I couldn't solve it right away, I'm trying to find a way to do it with some assumptions that would simplify the equations. So, here are my ingredients. So, as a matter content for the universe, I just neglect the neutrinos. Consider there are baryons, photons, and whole dark matter. And then, schematically, in the universe, we have inflation, which sets the initial condition for the zeta, for the perturbation. Then we have a radiation-dominated era. Then we have a matter-dominated era. And a bit after the equivalent between radiation and matter, we have recombination, and then matter becomes transparent, last scattering surface, and then light is propagating through now, and with the ray. So the plots I'm going to show use this reduced scale factor, y, which is the scale factor divided by the scale factor at the moment of equivalence. So at first order, the results are well known, but I plot them. At first order, this is for a given mode, and in dashed line, this is for a larger given mode. So what we find at first order is that the gravitational potential, so the perturbation in the metric, is dumped once it enters the Hubble horizon. So here it's a mode which enters the Hubble horizon before equivalence. Here it's in log scale, so equivalence is here. Everything which is on the left is radiation dominated. Everything which is on the right is matter dominated. So what you find is that the gravitational potential for modes which enters the Hubble horizon before equivalence, it dumps, and it's even more dumped that the mode is larger. Then for the perturbation of the energy density in the radiation, it's also dumped for different reasons. It's not because of viscosity. So here you see that it's oscillating, but the amplitude of the oscillations are reducing just because of this viscosity. So in the equation I showed you, in the earlier equation, it's because you have a leakage of energy density into velocity, a leakage of velocity into anisotropic express, and so on. So this leakage explains the dumping. And if you have a larger mode, then the damping is even more efficient. For the baryons, it's the same because radiation and baryons are coupled through their interaction. So the same that you have the damping, and this damping is even more efficient that you have a large mode. But here it's for cold dark matter. That's the perturbation in the energy density of the cold dark matter. So you see that here the equivalence between matter and radiation is here, but even before, when the mode enter the Hubble horizon, then it starts to grow. The perturbation starts to grow. So it's actually a logarithmic growth here. And then after the equivalent, it grows even faster. So it grows before matter domination, because cold dark matter can collapse and is not pulled by radiation. And then after equivalence, it collapses even faster. So the main idea in the assumptions for solving the second order evolution is to assume that we could, for large mode, neglect the potential because it's sound. We can neglect the perturbations in the energy density of radiation environments, but the dominant terms will come from the perturbation in the energy density of the cold dark matter, just because it collapsed earlier and it's not pulled back by.
And by growth, you mean the magnitude growing, right? So it starts at 0 and then.
This is not long, yes, it's not at 1 and then here.
If somebody is confused.
And the potential and dark matter are not related to a Boltzmann equation?
Sorry?
You don't have the potential and the dark matter density related by a Boltzmann equation?
Yes, they are, but for a large mode, then you have a k squared in both.
Yes,
here,
k squared.
You see, it's not, but actually it ends with a non-zero value.
That's right, and then all you're seeing is a change of k's between those two.
Yeah.
But if you see oscillation there, shouldn't you see a similar oscillation? At least, you're saying the oscillation is damped by the fast growth.
Yeah, the contribution
dark matter, you just don't see it anymore because it's growing too quickly.
Sorry?
Well, I mean, if you've got an oscillation in the potential,
yes,
there should be a corresponding oscillation or wiggle in the dark matter as well.
But here it's you're dominated by radiation, so okay, it comes also from the oscillation here, and you're also the distribution of baryons. That's why you have this tiny oscillation, because there is like 1/5 of baryons and 4/5 of cold dark matter. So if you look at the amplitude, that is. I mean, what is from here to the average of the oscillation is due to cold dark matter, and the oscillation that is due to baryons.
Or photons. I guess like a photon dominates the mass until 0, so I guess a photon doesn't want to dominate your graph potential even.
What?
Right, until modulation equality, it's the photon.
Oh, yeah,
that
here it's
dominates
after
potential.
14, yeah.
And then afterwards, it's definitely.
Yeah. You're bothered by the fact that you get big number here?
No. I just simply, for those who think that the curve which falling down is increasing, not decreasing. Right?
Yeah, sorry, yes.
Because
It's
the magnitude grows.
yeah, sure. Magnitude. So then my idea is that since cold dark matter is the only thing which actually grows, then it's the collapse of dark matter which will lead the second order. So it's the nonlinear evolution of cold dark matter collapsing in a matter-dominated universe below the Hubble radius. It's something which is well known. It's Newtonian perturbation theory. Also Bernardo is the expert in this. And so it says that the second order perturbation in the cold dark matter, it's a kernel multiplying the first order perturbation of the cold dark matter. And since this is increasing, so this is increasing even faster. So of course it's well known that it becomes nonlinear and you have the collapse of the structure. So this collapse of cold dark matter, that's the thing which will dominate the potential through the Boltzmann equation at small scales. And then it's what will guide the coupled systems of photons and baryons at first and at second order. So at first order it's well known, but at second order it's going to be even more true. And that's why we can make the following assumption. We solve the equation at first and second order, but what we do for baryons and photons, baryons and photons, we don't need the nonlinear response. So we just throw away the quadratic terms because they will involve baryons, they will involve potentials, and all these quantities have shown that they are too small. We only solve for the quadratic terms, that is the nonlinear evolution, just for the conservation earlier equation of cold dark matter, and of course in the Einstein equation in order to get the Boltzmann equation correctly. So the simplification is just to throw away all the work I did before to work out the quadratic term and nonlinear term in the evolution of radiation, and just keep the linear term, but to solve correctly for cold dark matter and Einstein equation.
So you're in a Boltzmann equation. I'm trying to understand. So you have Boltzmann equation. So what is calculated in second order? Only left-hand side, only genetics, or
No. Well, the problem is when you do calculation, you want to collect on the left-hand side the linear term, on the right-hand side the quadratic term. So for Boltzmann equation, you put u-vil on the left-hand side and collision on the right-hand side. So in the left-hand side, in the u-vil, then you have two parts, linear and quadratic, and we drop the quadratic. And the collision the same, linear and quadratic, and we drop the quadratic.
One second. So your Boltzmann equation is strictly first order, or there's some non?
We use for the second order variables the same equation as for the first order variables.
Yeah, but no, I'm just confused what approximation you're making. So did you get? Okay.
So okay, I can show you in the next slide.
We understand general formulas. It's clear. But now you said about
so when you solve the Boltzmann equation in the approximation of tight coupling or almost tight coupling,
okay,
you can show that it's equivalent. So if you take the continuity and the equation, you combine. It's almost equivalent to this equation, which is the evolution of oscillation, damping, and here you have the forcing term, which is the potential. Sure. So at second order, here what I've shown away is plus quadratic term.
But quadratic, you mean quadratic in the first order?
Quadratic in perturbation, quadratic in first order perturbation. And so what I said is because these terms always involve either potential or radiation perturbation or variant perturbation. At small scales, they can always be neglected, and formally the equation is the same. But the main difference, so formally it's the same equation, but the main difference is that this potential, at first order it's the same equation where you put the first order everywhere. And at second order it's this one, or as thrown away the quadratic term. But what is inside this potential, what creates this potential is completely different. This comes from the collapse of solar matter. So it's formally the same, but it's physically completely different. And so, because it's formally the same, the result is formally the same, but physically completely different. So, for when the viscosity is very efficient, you can see directly from this term. Just imagine that this is an important damping. That the solution is delta R over 4 plus phi, which goes as a limit to minus R phi, and then at second order it's going to be the same limit. So when the viscosity is very efficient, then the cycle effect, which is delta over 4 plus phi, is driven toward minus R phi, and at second order it's going to be the same. But the main difference is that what is inside the first, what is inside here and here is completely different.
So in principle, this delta R2 will be excited at inflation in a quadratic order, and you are saying that you are propagating it essentially with the same equation as the first order, except potential, which is potential being reflecting halos and all that stuff.
And except for that matter. So the continuity and variation equation for that matter is completely nonlinear.
No, I thought you were saying the opposite. I thought you were saying that all the second order is dominated by the nonlinear growth of the CDM first order squared, so that you can ignore the inflationary second order term.
No.
That's what you think? No.
No. Here in this work, just because I wanted to know how much comes from the evolution, I've taken a completely Gaussian initial condition.
Yes, so there's no maximum inflation.
That's an equation which is valid whatever initial conditions you put.
Yeah.
You can put initial conditions delta R equal to 0, means there is nothing on inflation. And then you will see what is generated along. And it will be through phi 2, which fills Kodak matter. Or you can put non-zero initial condition, and then you will propagate your whatever you have.
If you change the initial conditions, it will change what is inside here. So you will have the potential coming from the initial condition plus the collapse of Kodak matter. So on small scales, then using the Poisson equation into this collapse of Kodak matter, then you get that the second order potential is related to the first order potential by here there is convolution and this kind of, and it's increasing with time.
Just one last question about your approximation. So you're saying terms which you're neglecting is like delta R1, phi 1, etc., etc.
Yes.
In nonlinear, well, yeah, maybe it's right. You have non-linear phi 2. I'm wondering that the gradients of phi 1 can be large, although phi 1 is small. No, there's no things like that. I mean, potentials remain small throughout the story, but it develops kinks.
In the Boltzmann equation,
but not
you have no. Okay,
it's probably okay. But,
this, I think in the Boltzmann equation it's not a problem, and then in the Einstein equation I keep this grade.
Right.
So,
You think this k of k1 and k2 is not a delta function of k1 plus k2?
it's a what?
It's not a delta function of k1 plus k2?
Delta function?
It's not a delta. You don't have to have k1 plus k2 equal to k.
Sorry, that's what I was saying. Here there is a convolution, just to fit the bit, there is a convolution over k over all k1 and k2 whose sum is k.
Oh, yes.
It's like the formula I've shown in the beginning, where there was this convolution and the delta function. So everything I will present here, there is always this convolution implied. So what I'm going to present in the next slide is, so this is what we expect to reach asymptotically, but if we integrate numerically, then we recover the collapse of, we recover the same feature. So on large scales, we have the directional potential, and then here it becomes below the Hubble radius, then matter dominated, and then that's the point where the directional potential is completely shaped by the collapse of full dark matter. It's the same, completely shaped from that point to the by the collapse of full dark matter. Here it's the Zakharov effect and the Doppler effect. And you see that in black it's the Zakharov effect, in red it's the Doppler effect. So what you find at small scales, that the Doppler effect is completely damped, second order. And the Zakharov effect, it's damped, but reaching an average value, which is non-zero. That's what I said in this slide. It's reaching minus R5. And plot here in dashed line is minus R5. So you see that it's driven towards minus R5. In gray here, it's at the last scattering surface. Then it's imprinting the last scattering surface, and then the approximation for near tight coupling is wrong, but it doesn't matter because now it's imprinted in the last scattering surface. And it's just a matter of knowing how we observe what's imprinted in this LSS.
What is the difference between left and right?
It's just a small mode. It's a given mode,
Yes.
and it's a small mode. So this will correspond to the scales like around
different
let's say L equal to 2000 once projected, and this will correspond to like L equal 3000, very, very small scales. Just to show that it's the smaller the scale, the better you reach this minus R5 limit. If I had shown a scale which is large, it would never reach this limit. The viscosity would not be efficient enough to damp the situation before that surface. So now it's just a matter of knowing how it projects. So this is one node. You just have to go to spherical harmonics. So at first order, all this process of starting from the initial condition, propagating through the temperature, projecting the sphere of the last scattering surface, this gives you the transfer function. And then all second order, well, with this approximation, gives you the second order, sorry, what do I put it here? The second order transfer function. And now if you also add the primordial curvature perturbation, you will also have the term which comes from the homogeneous equations, which is the linear transfer, so the function of the primordial second order curvature perturbation. And in the bispectrum, which is a combination of the statistical average of three-point function, then we'll have either a contribution of this, and as I said at the beginning, or a contribution of this. Now it's we are close to the point where I'm going to compare these two effects. So what I want to compare is this one to this one. So what I took a model with a constant FNL. So in the beginning I showed you that FNL could be momentum dependent. So here I've taken a constant FNL, local type, and for different values of FNL in colors, this is the bispectrum you get for different values of FNL in the equilateral shape. So red is FNL equal 1, FNL equal 10, 100. And in black, that's the other term, the term coming from the evolution. That's the bispectrum generated by the term coming from evolution. So you cannot really trust this part of the plot just because all the approximations I said I was using, downbeing because of viscosity, they are not really valid below L equal 1500, just because viscosity is not strong enough. But beyond this point, we are in the limit where these plots are valid, where this behavior is valid. So beyond the 1500, then you can see that evolution or an FNL of above 10, like 20, but it didn't measure precisely, it has equivalent contributions. So it's interesting, but it's not enough. It's interesting because it means that evolution can matter. But it's not enough for many reasons. First, since I relied on small scale approximation, what I plotted here is the equilateral configuration, just because I needed all the L's in the bispectrum to be large. So what people are using when they want to detect non-Gaussianity of local type, they use squeeze configuration. So it means that all this work has to be done this time completely correctly with the full numerical integration without any assumption, just to know what is the evolution in that case. And also because the effect is the effect of being equivalent of 15 equals 20 is only on very small scale, and most part of the analysis is going to be done between 500, well, 0 up to no more than 2,000. So having a result that is valid only after 1500, it means that qualitatively it means that evolution matters, but quantitatively still it means that we need to solve completely the full nonlinear Boltzmann equation. So in the way I presented the things, I told you how to derive the exact Boltzmann equation. And then I said how I solved it. It's just because I did it backwards. So I solved it in the simple case, and then I derived the actual full equation. So the next step now for me is to solve it numerically, and it's a very long task, so that's it.
So when you, I just want to follow the approximations that make it easy in the small scale limit.
Yeah.
But the decoupling of, I mean, it is still true even at low L that you can consider all the forcing to be dominated by the cold dark matter, right?
Low L or large L?
At low L. The question is, when you go to low L, which is where this doesn't hold, you're saying life gets a lot harder because you have fewer of the approximations that hold. But the first one is still okay, right? So the delta CDM is much bigger than any other, is independent of L.
No, because you need to collapse during a radiation in zero.
So somehow at recombination, unfortunately, CDM doesn't dominate that completely gravity.
Exactly.
You have radiation variance contributing.
So what is the error that you qualitatively that you incur by neglecting variance?
Oh, on small scales?
Yeah.
Oh, it's about
20%.
Yes, exactly.
And I guess the other question is, what are the competing methods out here for doing this type of calculation?
Sorry, I don't understand.
What are the competing methods out there for doing this type of calculation?
Competing method. I went to Boltzmann in November, and they wanted to do the same thing, but in a real space instead of doing everything for a space. So there were more in. They wanted to do in Portsmouth.
I see.
They wanted to do it in real space, so in order to look at the non-Gaussianity in the PDF rather than in the 3-point function.
This no one has really pushed this through to completion.
Sorry?
That's the state of the art.
Yeah. I'm a dummy from the high gas physics.
And there's also a team of Italians who did this.
Do you agree?
Yes, I agree. They did their paper and copied it. So yes.
Now, if one just did what people did in ancient days, if one just took ensembles and evolved them and just did realizations instead of expectation values, is that really much less accurate or less tractable or more expensive? Or?
Sorry.
Well, instead of trying to compute the evolution of
Yes.
the ensemble,
Mhm.
you could just say I generate a random Gaussian random field and just solve my equations to any order I want. Right? I can just solve my Boltzmann equation numerically in a simulation, three-dimensional.
Oh, you mean not relying on solving equations, just doing an n-body code? And
Yeah, whatever way, a Boltzmann code, 3D.
I don't know if it would work along the LSS. Usually it's what you do in Newton, because in order to simplify all these codes, you need Newton and gravity. And here, around the last Hashing surface for large
You need
codes.
second order gravity only, right? So you only have to get a non-linear gravity solver that on Tuesday we heard has been implemented.
But what you mean is doing numerical integration without relying on Newtonian limits?
Yeah.
I haven't heard this been done before. I think it must be quite complicated now.
Well, in general, yes, but Octavian Schmidt, for example, has been evolving nonlinear gravity for other reasons.
Oh, right. But also one of the points of doing this is that when you're in Fourier space and you compute the 3-point correction function, you never have to compute the integral of momenta. So it's very straightforward once you have it in Fourier space, just to transpose it in the bispectrum. So for the bispectrum, I think it's purely numerical integration will be performed. But for PDF, yes, probably. I don't know.
So your prediction on Planck is definitely going to see non-Gaussianity or else gravity is wrong.
In Planck evolution,
Planck has to see F
Well,
and
that's-
in an equilateral shape, it's like 25 or it's about the limit of resolution for equilateral.
I thought the resolution was like 5 or something.
It's for using squeeze
Oh, it's
triangles.
But is the shape dependence of your bispectrum, similar to equilateral, or is it similar to squeeze? I missed that part, I guess.
If it, sorry.
Is the shape dependence of the bispectrum, as you calculate second order, so is that similar to?
I cannot know if it's how it looks like in the just with this approximation. I cannot know how it looks like in the squeeze state because it's not in the right limit. So it's only I can only know what it looks like in the equilateral shape. So you have a bump in the equilateral shape. So actually the shape of the bispectrum is the shape of this kernel, which is the kernel of the collapse of the matter in matter era. So it's something which is has a bit in the center, which is really probably shape.
Okay. Do you have any guess?
Sorry?
Do you have any guess?
The difference between squeeze states and equilateral limit?
Yeah.
The basic numerical integration I did with simplifying a lot, but just trying to see it's completely different in squeeze limit, the results. And cold dark matter is not the term which dominates the conflict.
That's just the level of effect get bigger.
Well, smaller, I think he's saying.
Small.
Yeah. I don't know.
Smaller for squeeze.
The effective evolution, I think it's going to be smaller. Well, for sure, I don't think. Well, usually nonlinear effects are small scale. So in the squeeze state, you have only one mode, which is small. So at least if it's the same physics, but it's not, it would be.
Yes, squeeze state makes it more small.
But also, the physics behind squeeze states is non-total, so it cannot be triggered by the collapse of the collapse matter. So basically, in this sum, I think the term coming from the linear evolution of the prime model is still the one which dominates. That's my guess, but it has not been shown. Hmm?
That's just a function of the
Yeah.
Then to what extent, given this, what extent can you take this effect out?
I mean,
Does it matter to our ability then to measure the primordial?
If it's an equilateral, yes, for sure. It depends on the type of primordial motion.
Does it matter after you take it out? Will you be able to have
Yes,
it correctly?
Clearly, that's the point of. That's exactly the point of having a numerical code. You observe the CMB, you see all these bumps, and you want to go back to the primordial parameters. So that's the same. You see a bispectrum, and you want to be able to go back to.
But there are foregrounds, of course, we generate.
Oh yes, yes. And then starting from 1500, you have
But this
between
particular
Lenzing and
program,
Sunayet and
Monte Carlo, some effective transfer
Like,
function.
even on larger scales, I mean, there were still programs limiting your ability to measure the primary. Right. I mean, so.
Yes, it's. So I agree. It's very true. You have all these
Right,
programs.
so your level seems like smaller than smaller than the programs I thought, right? So one thing I thought, gives you like larger bispectra than this for.
You thought you would get a lot of percentage.
Well, for squeeze, I thought it was like 10-ish. I mean, but for like for these more equilateral lines, isn't it larger?
Okay. But do you really have? Are you really hopeful that you can broaden your approximation on the lower L? You can actually.
In that case, it would not be approximation. It's just just that the coupling between in the Boltzmann hierarchy at first order you have a coupling between L and L plus 1 and N minus 1. And the M's are not coupled. That's why we solve for scalar, M equals 0, vector, and tensor. And at second order, there's coupling between L plus 1 and L minus 1, but also between M plus 1, M and M minus 1. So it spills everywhere. And so you need to solve this Swift system and to be sure that it's stable, the solution defined.
Okay, I think we should stop here. So I know he should be around till
tomorrow.
So tomorrow we will be here, and tonight we are also taking him out for dinner. So I'll talk to you later.